As we learned yesterday, Snell's law of refraction tells us at what angle light will be bent as it enters a new medium. The equation is n sub 1 times the sine of theta sub 1, which is your angle of incidence, equals n sub 2 times the sine of theta sub 2, which is your angle of refraction. Okay, now, just to review, when light goes into a dense medium, it bends toward the normal. When it leaves a dense medium, enters a less dense medium, it bends away from the normal line. So let me add to this now. We have what's called a critical angle, theta sub c. And a good definition is that theta sub c, the critical angle, is when you're in a dense medium. You start in a dense medium, you're leaving the dense medium, going into a less dense medium, in which theta sub 2 becomes 90 degrees. Let me do this mathematically first, and then I'll demonstrate it. In other words, if theta sub 2 is 90 degrees, that's one of the conditions for the critical angle, or determining the critical angle. Essentially, that's the only thing I have to plug in. What you'll end up with, going to the top here, is n sub 1 sine theta sub 1 equals n sub 2 sine 90 degrees. When we plug in that 90 degrees there, the sine of 90 is 1. And at that point, theta sub 1 should really be called the critical angle. In other words, theta sub 1 now is the critical angle when theta sub 2 is 90. So I should have put in the following: n sub 1, that's n sub 1, sine, instead of theta sub 1, now it's called the critical angle. Theta sub 1 is now the critical angle, and n sub 2 times the sine of 90, that's just n sub 2 times 1, so that's just n sub 2. Well, in other words, the conditions, or the equation, the critical angle equation is the sine of the critical angle, mathematically, is the ratio of n sub 2 over n sub 1. So we call that our critical angle equation. Critical angle equation. All right, now, before I give you a demonstration lower on the page here, to give a little bit more meaning to the critical angle, let me review a couple of Snell's law problems here. I haven't drawn the diagrams yet, but let me just draw these for you because I want to give you some more advanced ones than I gave you yesterday. So for example, number 1, this is not critical angle yet. This calculated theta sub 3, and I haven't labeled these yet. In a situation, I'm going to make up a situation, for example, like this. Let's say we have some kind of surface that's at an angle, and it says n sub 1 is 1.5 and n sub 2 is 1.1. This is going to represent, let's say, light going sideways, hitting this surface at an angle. And what I'm going to be calculating at the end here is this angle right here, theta sub 3. I'm going to call this theta sub 3. Now, when you have your light beam, and we'll be doing this in lab, that's intersecting an interface between two surfaces, the first medium, n sub 1 here, is 1.5. It's a denser medium. So the index of refraction says n sub 1, the medium you're starting in, has an index of refraction of 1.5. That's n sub 1, labeled there on the left. And the second medium is less dense. It's 1.1. So you're going into a less dense medium. This could apply to the critical angle. We're not going to do it yet. But bottom line here is if I draw the normal, and when you do these diagrams, you always want to draw these normals. That's a line perpendicular to the surface between the two mediums. So that's the normal once again. When that light, that ray of light, goes into that medium, since we're going from a more dense to a less dense medium, whenever you change speeds like this, the light beam is going to bend. So that blue beam of light is not going to keep going to the right, but it's going to bend away from the normal because we're leaving the dense medium and we're going to a less dense medium. So the bend is going to be more like this. Let me use blue. More like this. That's supposed to be a ray, where this is theta sub 2, measured from that ray to the normal. This over here really is theta sub 1. Once again, both angles, theta sub 1 and theta sub 2, that we will use in Snell's law are measured with respect to the normal. Theta sub 3 will be related to theta sub 1. We'll deal with that later. But essentially, I'm just going to do a straight plug into Snell's law, because I'm told that theta sub 2 here is 66 degrees. So this angle is 66 degrees. So we're going to have n sub 1 sine theta sub 1. I'm plugging into Snell's law here. I'll use red. N sub 1 is 1.5 sine theta sub 1, the material I'm starting in. I don't know what theta sub 1 is quite yet, equals n sub 2, which is 1.1, times the sine of theta sub 2, which is 66 degrees. So I know everything in that Snell's law except for theta sub 1, and if I go to my calculator and plug it all in, theta sub 1, the angle of incidence here, should come out to be, I believe, 48 degrees, if I calculated that right. That's my angle of incidence. Well, I need to get theta sub 3. Well, theta sub 1 and theta sub 3 are complementary. They add up to 90. So I simply take 90 minus 48. I'm a little out of room here. My final answer is theta sub 3. Theta sub 3 is 42 degrees because it's theta sub 1, 48 degrees. Well, 90 degrees minus the 48 degrees, which is 42 degrees. That's the angle I'm looking for there. Here's a second example. Let's say we have a vertical interface, like a window. And to the right here might be air. It's probably not air, but it's some medium that we don't know. I'm going to call this n sub 1. N sub 2, a different medium, represents, like, say this is going to be like the window, the glass. I know that n sub 2 is 1.44. I was given that in the problem. Let's say we have a ray of light that's hitting this surface, this interface. The first thing you want to do is you want to draw the normal. Let me use black. The normal line, which is perpendicular to the interface. Since the interface is vertical, the normal line is horizontal. That's the normal. Alright, so I know in this case that theta sub 1 is 31 degrees. I was given that in the problem. This is 31 degrees measured with a normal. And theta sub 2 is 25. So the angle theta sub 2 is less than, so I'm bending toward the normal. So I know that N2 is a thicker or denser medium optically than N1 because I'm bending towards the normal. Theta 1 is 31, theta 2 is less. So once again, the final direction of the ray is bent closer to the normal. So I made that second angle with the normal smaller, and that's 25 degrees. That angle right in there is 25 degrees. It's hard to show that here. 25 degrees. That's thin sliver of an angle, smaller than 31. So once again, I'm just going to plug in this Snell's law. N sub 1, which we don't know, N sub 1 sine theta sub 1, the original entering angle is 31 degrees, equals N sub 2, which is given 1.44, sine of theta sub 2, which is 25. Alright, so I know everything except for N sub 1. I go to my calculator, plug it all in, and N sub 1 comes out to be, hopefully I did it right, 1.18. You could pause and check that. N sub 1 has to be less than N sub 2 because you're bending toward the normal as you go into the denser medium, which has a higher index of refraction, 1.44 versus 1.18. Now let's talk a little bit more about critical angle. I gave you the formula at the top that the sine of the critical angle is N sub 2 over N sub 1. I'm going to keep reminding you here that it's very important that the only way you can have a critical angle if you're in a dense medium and you're transferring or crossing over into a less dense medium. Here are the examples. We're going to go from water to air. It's a very common example. But here's a progression of possibilities. On the left hand, there's three diagrams here. In the first diagram, we have a ray of light that's at angle theta sub 1. Kind of missed it there. And it bends. There's the refracted ray. It's supposed to be on top of what they've given me. Theta sub 1 and theta sub 2. Because theta sub 2 is bigger than theta sub 1 since you are going from a more dense to a less dense medium. And what happens here, though, is if you have a light, a laser, any kind of light beam that's pointing from underwater towards the surface, and you increase theta sub 1, well, what's going to happen is theta sub 2 gets greater as theta sub 1 gets greater. But theta sub 2 eventually is going to make it up to 90 degrees for a given angle theta sub 1. So the middle diagram here shows you the critical situation. Let me show you an intermediate situation. Let's say I have another situation where theta sub 1 is bigger than the first diagram. Let me use black for this case. Let's say I have a theta that's not quite the critical angle. And I draw my normal. Right? So this angle right here that I just did with theta sub 1 is bigger than the initial example with red. So my theta sub 2 now is going to be greater than it was before. So you might have a theta sub 2 or a bent ray that looks like this. So here's my theta sub 2. It's approaching 90 degrees. As theta 1 gets bigger, theta sub 2 approaches 90 degrees. And what's going to happen as you start to approach the critical angle, there will be some slight reflection that occurs at the boundary, at the point of refraction. So even before the critical angle, there's going to be some reflection. That light will start to reflect, and I'll use a light red reflection here for this black example. There's going to be a little bit of reflection before the total reflection that's going to be in the last diagram. So this angle right here, theta sub 2, is a reflected angle that's going to equal theta sub 1 in the case I just drew for you. So theta sub 1 is going to equal theta sub 2 for, well, I should call this theta sub 3, because theta sub 2 I have for the refracted angle. So theta 1 and theta 3 are angle of incidence equals angle of reflection. Theta sub 2, the angle of refraction at the top there, is going to be bigger than theta sub 1, but it's approaching the critical point. All right, I'm going to pause and erase that for a second. Okay, so when you get to the critical angle, theta sub 2 technically would be 90 degrees, but in practice, theta sub 2 can't equal 90 degrees. That refracted ray there cannot follow that surface at the top. It cannot skim along the surface. So what happens at the critical point when theta sub c is at the critical angle, theta sub 1 is the critical angle, that ray will not follow the surface. It will reflect. All right? So you're not going to have a ray that technically follows the surface. You're going to get a reflected ray, theta sub 2. Okay, in this case, theta sub 1 or theta sub c equals theta sub 2. There's going to be angle of incidence equals angle of reflection. There will be no refraction here in this diagram. So you see that in the final diagram, you have what's called total internal reflection, which is very important in fiber optics, as I'll show you here in a second. So the fiber optics cables that I'm showing you here on the right, it's like a piece of glass. It's got to be transparent medium. So on the right here, the fiber optics that we experimented with in class, you shine some light into that cable, and light travels in straight lines. Here's our fiber optics cable over here, and it keeps reflecting because each reflection, it's like a mirror, but it's not a mirror. It's reflecting because of total internal reflection, because the light cannot escape the dense medium because the angle is exceeded. The angle of incidence is greater than, equal to, or greater than the critical angle. There can be no refracted ray because the refracted ray can't go beyond the 90 degrees. So total internal reflection occurs when theta sub 1, your angle of incidence, is equal to or greater than the critical angle. The critical angle is when the total internal reflection begins. All right, calculating the critical angle between two substances is very easy. Like here, it's like, what's the critical angle between crown glass water interface? Well, it's just a straightforward kind of plug and chug. The sine of the critical angle is going to be n sub 2 over n sub 1. And you have to start in glass. You can't be in, actually I think I have in the example, I want air on your notes. I'm going to do the air-water interface like I have in the above page. I'm going to do air-water interface. You have to be in the more dense medium, like water to air. You cannot have a critical angle going from air to water. But here I just look it up. The sine of the critical angle, theta sub c, will will be n sub 2. N sub 2 will be the air. Air has an index of refraction of 1.00. Water is 1.33. That's the index of refraction. You look it up. You don't need to memorize that. You go to your calculator, do the inverse sine of 1.00 or 1.33, and you end up with the critical angle for the air-water interface. And what's meant by that is you're in the water going towards the air. Cannot happen from air to water. It comes out to be 49 degrees. So if you have light underwater heading towards the surface of a smooth water tank or pool, the light will not escape the water if the angle of incidence is greater than or equal to 49 degrees. That's total internal reflection.